Hello, I gave you this question in the previous video, and so you need to calculate the median by calculating the cumulative distribution function. So cumulative probability is simply adding up the probabilities 27 and then 27 plus 34 and then 27 plus 34 plus 16 and then plus 14 and then plus 9. So at the end it becomes 100% and it always increases. And among them, after calculating the cumulative probability, the smallest value over 50% is 2, right? So 1 does not exceed 50%, so it fails. And then the next one exceeds 50%, and this is the smallest. So automatically 2 is the median. So 2 is the median household size. Okay, now I'm going to compare the mean and the median. Why we need to use the mean or why when we need to use the median. So simply, almost always the mean is more common. The mean is like in general more widely used and has excuse me, better properties, mathematical properties, and easier to calculate and easier, excuse me, easier to handle. However, there is one critical problem. It is that the mean is severely affected by outliers. If there are outliers in the data, the mean can be contaminated. It may be misleading. So, uh, so you have to think about using the median if you suspect there are outliers. On the other hand, the median is better than the mean in that it's less sensitive to outliers. It's more robust. And however, it is less tractable, so less popular, frankly. So, simply speaking, if you want to use one measure of center, I recommend the mean. However, if you have to worry about outliers, you have to think about outliers, and if you think your data have outliers, then calculate the median too, right? Median cannot replace the mean, but median can complement the mean. Okay, and the outliers, then outliers cause problems, and it is particularly common in economic data. That's why economists consider the median more seriously um, in than statisticians. Think about this hypothetical example. Suppose that you are interested in the income distribution and you surveyed 10,000 households, which is a really good survey. Suppose that you have a very nice survey of 10,000 households and you obtained that the mean household income is 0.1 million. 0.1 million is the mean of 10,000 households, but you'd like to make it better data, so you surveyed another household, and unfortunately, the additional household, the next household was Bill Gates. By the way, I had to update the he's update his divorce, and maybe Elon Musk or Warren Buffett or Jeff Bezos. Maybe just think about anyone, any rich. Anyhow, you met a super rich here, and his income, Bill Gates. In case of Bill Gates' income in 2019 was $12 billion, according to Business Insider, right? Uh, so if you take it as a face value, then just take 12 billion observation. Another observation is 12 billion. And if you recalculate, including Bill Gates, recalculating the mean household becomes 1.3 million, which is more than 10 times, 13 times greater than the mean. So this is hypothetical data. So zero point 0.1 million is just a simple number, imaginary number. If the actual number should be smaller than this. So so just like you already have 10,000 households, but 1 out of 10,000 makes the mean like 10 times larger, which is not normal. It's something is not right. So extremely small number of extreme outliers can mislead your analysis. It looks like, oh, everyone is so rich, but actually no. The only rich in the data is Bill Gates, right? Um, this is Bill Gates is the outlier who is extremely outlying, so it causes the problem. And in our previous example of states, also you see outliers. California is an obvious outlier. Maybe you may think Texas is also an outlier. There is no clear definition of outlier, whether who's outlier and who's not. But obviously, these guys are outlying. So it's not. So they may they may contaminate the average. So to see how much they change the data, so if you use all 51 states, the mean and median was calculated like this, right? We calculated them earlier. And suppose that from the data, you think California is an outlier. So you deleted California from the data. So there are only 50 states. Then the mean and the median would change from if you recalculate them in the data without California. Without California, mean becomes 5.4, median becomes 4.9, 4.09. So what you want to see here is how much California changes the mean and the median. So simply by deleting California, the mean dropped by zero point 0.6, but median dropped by 0.25. So as you can see, the mean is more sensitive. So if you add or drop California, the mean changes much more than the median. Similarly, if you additionally drop Texas, also the median changes by 0.4, but also the median is changing by 0.24. So like as you can see here, the mean in each case, the outliers, California and Texas, cause changes affects the mean much more than the median. So in that sense, the mean is too sensitive, but the median is more robust. So they like analysis based on the mean could be very different from the analysis based on the median. So have to be careful when you have outliers. In general, outliers can be seen from the histogram. So if you have draw a histogram, it's about the tail. So in this case, outliers, there is a long tail on the right side, then they are outliers. And outliers on the right tail, in this case, mean would be larger than the median because those outliers will increase the mean more than the median. On the other hand, if there are outliers on the left-hand side, then the tail is long on the left-hand side, and then in this case, the mean would be smaller than the median. So the mean drags down the outliers drag down the mean more than the median, so the mean will be smaller. So anyhow, based on the shape of the distribution, you can tell what where the outliers are, and and also you can check that using the mean and the median. And this is particularly a problem in economics, as I said earlier. So in general, like natural sciences, outliers are rare. Say you never see a person 10 times taller than the average, right? Or you cannot see like something, say I have a cell phone here, but you never see a cell phone 10 times larger or 10 times heavier than what it has to be. So this much kind of errors do not happen in reality, in natural science. However, in economics, it does happen. Something like super rich, for example. I think I know many people who are 10 times richer than me. And also, you can see that Apple, Apple, Microsoft, these firms are like 100 times larger than the average, maybe. And when stock market crashes, then it crashes like, I don't know, like exponentially, uh, at an exponential rate, which is much faster than its usual volatility. So outliers are very common in economics. I will show you a shocking example. This is this is analysis of growth. So here it's a data from New York Times. So it shows a graph from 1975 to 2009. There are two lines. The red solid line is real GDP per capita. You may understand it as the mean. So by definition of the GDP per capita is the mean, right? It's GDP is the sum and divide by population. That's GDP per capita. So it's the average income per person per household, or and this is this is median household income. So this is the mean, this is the median. So if you look at the mean, oh, GDP, the income in the United States has grown a lot from about 100 to nearly doubled in the past like 40 years. However, if you look at the median, if you look at the median, the income increased only by about 20%, less than 20%. So they are so much different. So, and its interpretation is pretty clear. So in the past 40, 50 years, only the super rich became much richer. However, like average or like usual, typical households did not grow that much. They grew only like 10%, 20%, but super rich makes all the takes all the additional uh, takes up the growth. They take the benefit of growth. So this is a shocking difference between the average and the mean and the median. So as an economist, you should keep this in mind. So comparing the mean and the median may cause a big difference, and usually, and the interpretation is the outliers. There are outliers who are super rich. So there are the problem is coming from the outliers. And finally, so we just learned median as a measure of center. But using the same idea of median, so median is to divide the probability into 50-50, 50%, 50%. But it doesn't need to be 50%. So I can change the probabilities on each side, and we can define a different measure. So we are going to define measures of relative standing can be defined in a similar idea. I'm not going to go into the details, but just I'll give you the intuition. For example, like this. Instead of 50-50, you can split the probability into P and 100 minus P. Say 10 to 90, 20 to 80, like 80 to 20. Doesn't matter. You for any probability, you can define a measure. So that's called percentile. So in this example, in this graph, we divide the probability into 25 to 75. Then this cut point is 25 percentile, and interpret this as the bottom 25% value. Similarly, you may change the ratio to 75 to 25. Then this threshold cutting point is 75 percentile. So 75 percentile, and you interpret this as the bottom 75% or top 25% value. So in the same way, you can define any percentile, 1 percentile, 2 percentile, up to 99 percentile, right? So it's pretty intuitive, uh, and there are some common names, so mathematical definitions. Percentiles, simply speaking, roughly speaking, percentiles are defined this way. Probability smaller than or equal to the cumulative probability up to p percentile equals p%. So actually, it's not exactly equal, but roughly speaking, intuitively speaking, you can think the percentile in this way. And some special names. 0 percentile is the minimum, right? 100 percentile is the maximum. And 50 percentile is the median. So that they are obvious. And if you cut the data into 4 groups, they become 25 percentile, 50 percentile, 75 percentile. They are called quartiles. Quartiles because you divide sample into 4 groups. And first quartile, second quartile, third quartile. Similarly, there are many different names like quintile, decile, quantile, a lot of different similar names, but I think percentile is enough at this level. Okay, and uh, finally, final examples. And these percentiles are very useful in many examples. For example, in finance, if you're interested in finance, you must have heard about the value at risk, VAR. Value at risk is exactly what the percentile stands for. So probability of losing, say, I'll say $10 is 5%. So probability of losing 10 or more dollars is 5%. Then we say it's bottom 5% value, so 5 percentile. But in finance, we say it's 5% VAR. An infant growth chart. Infant growth chart. So say my son is 5 years old and he's 42 pounds. Then do you know if it's big or small? It is not informative. I say I just give you 40 pounds, 42 pounds. It does not deliver any meaning. But if I say he's at 25 percentile, then it's more informative. He's a little bit smaller than the average, but not that much small. It's kind of like his if there are 100 boys at his age, then he's 25th smallest one. So then it delivers more information, makes more clear comparison among the population. And inequality. If you study income inequality, usually the percentile is used. Like for example, 20-80 ratio. What is the ratio between top 20 and bottom 80 percentile incomes? So it's one of the popular measures to measure income inequality. And standardized score. Also, if you take a test and score, if I say your score is say like 20 out of 100, but it does not deliver anything. Like still 20 out of 100 could be the best score if the test was too difficult, but rather more informative is percentile score. So your grade is your test score is say 80 percentile. That means you are top 20%. So in these examples, percentiles are very widely used. So you already know you must have used some kind of percentiles in your daily life. So I am just formulating, I'm giving you more formal definitions and a bigger picture how to make the structure underlying the measures. Okay, this is the end of the chapter. I'm sorry it's going nearly 20 minutes, but anyhow, thank you for watching and have a I will start the next chapter, chapter 4, in the next lecture. See you later.